So welcome really to this latest video on 162 Maths, and in this video we'll be continuing with the theme of circle theorems with a focus on proving some of the circle theorems. Now the ones in question in this video we'll be going on to prove will be the arrowhead, the bow and the triangle inside the semicircle. Now, as well as being able to use the circle theorems and also quote the circle theorems at a higher level and at level 2 further maths, you will be asked to prove the theorems as well. So it's not going to be good enough to, for example, using the arrowhead as an example, to prove that this angle here at A is half the size of the angle at the center, or more formally known as the angle at the center of the circle is twice the size of the angle on the circumference. So what we want to go on is to prove that this is the case. So if this angle here is x, that this angle here is going to be twice its size. So let's have a look at how we go about explaining this. So the first thing we want to do is take an arrowhead as an example, and this is typically what an arrowhead would look like. Now the first thing we want to do is to draw a line from A to the center, and what we're doing by that is then creating two isosceles triangles. So if I just match that up there, so that's the very first thing that I'm then going to do. Now if I let BAO equal x, if I just call this angle x, then this angle here, then ABO is also going to be x, and the reason for that is because triangle ABO is an isosceles triangle, and the reason for that is because we've got two sides of equal length, because those two sides there are the radius. So this side here is going to be x. Then to work out what this angle here is going to be, so angle AOB is therefore going to equal 180 minus 2x, because obviously because angles inside a triangle add up to 180. So I can label this as 180 minus 2x. Now there's nothing more else I can do with that, so I'm just going to leave that as it is. So then if I then take the other triangle, and let's use pink, so let's call this angle y, then for the exact same reasons that because this is an isosceles triangle, as AO and OC is the radius of a circle, then angle, so then if I then, let me just write this down, so if OAC equals y, then ACO also equals y, because the triangle AOC is isosceles. So this angle here is also going to be y, and this angle here therefore is going to be 100 minus 2y. Now from that, what I can then do is work out what this angle here is. So therefore angle BOC is going to equal, well, angles around a point add up to 360, so it's going to be 360 minus angle BOA, so that's going to be 180, if I just put that in brackets, minus 2x, and then I minus the pink angle, which is 180 minus 2y, and that should be the case. So then if I then go on to simplify this, I get, and let's use a different color, let's go for purple. So here it's got 360 minus 180 plus 2x, because 2 minuses become a plus, minus 180 plus 2y. Then the 360 cancels out with the 180s, so all I'm left with is 2x plus 2y. So I can label this as 2x plus 2y. So here you can see that angle BAC, which is this angle here, is going to equal x plus y, and angle BOC, which is this green angle that I've got here, is equal to 2x plus 2y, or if I factorize it, as 2x plus y in brackets. Or what I can then do is represent that as two lots of BAC. So therefore I've then gone to prove that this angle here, so therefore BAC equals a half of BOC, or you could write it as 2BAC equals BOC. And there we go, we've proved the arrowhead theorem. Now the good thing to know that when you move on to the next theorem, which is proving that the opposite angle of the diameter of a semicircle is always going to be 90 degrees, or the angle inscribed in a semicircle is right angle, is virtually exactly the same as the one we've done for the arrowhead. Now, though this doesn't look like an arrowhead, technically it kind of still is. And the reason for that is because, now if I just get a pen, let's go for this one here. So if I was to drag point B along the circumference, and let's say I just imagine it's there, then that line there would be there. And if I drag C a little bit over here, so just call that C1, then that point there would be like so. And then if this was center O, then as you can see, it would therefore create a arrowhead. But again, what we do is we use the exact same, oh, just got rid of the triangle, so let me just get that back. And what we're going to do is we're going to use the same sort of method to then prove that the angle at A is going to be 90 degrees. Which kind of makes sense, because if it was an arrowhead, this is 90 because, and this is definitely going to be 180 because it is a straight line. So let's go on to put it into practice in terms of how we would prove that this angle at A is 90 degrees. So first things first, let's just put a mark of the center. Let's just say it's going to be here. And again, what I'm going to do is I'm going to draw a straight line from A to the center, like so. And again, we can do the exact same method as what we've done before. So here we've got an isosceles triangle. So if this angle here is X, then this angle here is going to be X, and this angle here therefore is going to be 180 minus 2x. If I was to call this angle here Y, then this angle here would be Y, because again that's an isosceles triangle because two sides are the radius. So then this angle here would be 180 minus 2y. So then to work out what this angle here is, again using algebra, it's going to be 360 minus, let me get that green pen back, minus this pink angle, which I just shaded in. Let's just put that in brackets, minus 2x, and then minus the blue angle, which is 180 minus 2y, put that in brackets. And if I then go on to simplify this, I get 360 minus 180 plus 2x minus 180 plus 2y. The 360s and the 180s cancel, so I'm left with 2x plus 2y. So if this equals 180 degrees, then x plus y equals 90 degrees. And if this angle here is x plus y, then angle BAC has got to equal 90 degrees. And there we've proved this theorem. So now let's have a look at our next circle theorem. So this theorem we're going to look at is the bow. Now the definition of the bow is that the angles subtended at the circumference sharing the same arc are equal. Now basically what that means is that when you've got a bow, that doesn't necessarily need to go through the center, where all 4 points are on the circumference of the circle, then these two angles here are going to be the same, and these two angles here are going to be the same. And what we're going to do now is we're then going to go on to prove why that is the case. Now you'll be glad to know that this follows the exact same thing with regards to the other two, in the fact that you should be able to see a arrowhead. Now it might not be obvious as to where those arrowheads are, but hopefully it should come into fruition if I join point D with the center. And let me just make that a little bit more accurate. And then do exactly the same by joining the center to C. And what you should be able to see is two arrowheads. So one arrowhead is here, and the other arrowhead is here. Now, we've already proved in terms of what the definition for the arrowhead actually is. So let's have a look at how we go about proving that those two angles there are the same. So if I then start by doing exactly what I did in proving the other two theorems, so I join a point from that point, then using this triangle here, if I call this angle here x, now because that angle there, that triangle there rather, is an isosceles triangle, then all of this is going to be also x, and this angle here is going to be 180 minus 2x. Now the same thing applies when I use the y. So if I look at the other, this is going to be y, that's going to be y, and this angle here is going to be 180 minus 2y, which has no significance at all but in relation to this. But then if I then draw, looking at the other arrowhead, and I call this angle here x, and this angle y, and this angle here, I'm going to get our colours, this angle y, so all of this then is going to be equal to y, and this angle here is going to be as they were. Now, one thing you should notice is that if I look at this angle of DAC, then that's going to be equal to x plus y. And if I look at this angle here, which is DBC, then that angle is also x plus y. So therefore, I've then gone on to show that they are the same. Now, when it comes to proving the bottom ones, what it kind of helps is if I kind of just get rid of, not all of the lines there. Let me just bring that one back. So let me just neaten this all up by getting rid of all the markings. And let's just get rid of all of that. And let's get a line back. Yep. And so looking at this, what we've then gone on to prove is that this angle is the same as this angle. And again, so let's just start by calling that x. Now, if I was to call this angle here, let's say b, then this angle here would also be b because they are opposite. So then to work out what this angle here is going to be, it's going to be 180 minus x minus b. And if I then work out what this angle here is going to be, then that's also going to be 180 minus x minus b. And as you can see, those two angles there are also the same. So it doesn't matter which one you go for, you're just proving that two angles that share the same arc on the circumference are equal, and that's exactly what we have done. So now let's move on to the alternate segment theorem. Now again, the alternate segment theorem is quite unique compared to the other theorems because when you are asked to give a reason or explain your answer, then all you'll need to say if you're using this theorem is just say the alternate segment theorem. To a point, you could even get away with using the acronym of AST. Now with the alternate segment theorem, it basically states that there are two equal pairs of angles. One is made at the tangent line, it's equal to the angle in the triangle on the opposite side. Now the most common sort of error where students make is basically thinking and linking this to the alternate rule with parallel lines. Now here, remember, it's opposite sides, you're not looking for z angles. In fact, it's the actual other angle that you're actually looking for. Now let's have a look at going on to prove that those two opposite angles in using the alternate segment theorem are going to be equal to each other. Now you'll be glad to know that by looking at this, you might think to yourself, well, how do I go on to prove that this angle here is the same as this angle here, and let's go for this angle here is the same as that angle there. Now for this, just like we've done before with all the other proofs, is what we need to do is draw a line from the points to like this. And as you can see, what I've done within the triangle, I've now created an arrowhead. Now also, we know that radiuses and tangents meet at 90 degrees. So going from this then, so if I then label this as what we know, if we call, let's call this angle here y, then this angle here is going to be y, and this angle here is therefore going to be 180 minus 2y. Now, remembering the rules of the arrowhead, that if this angle here is 180 minus 2y, then this angle here is going to be half of that, so it's going to be 90 minus y. Now, from this, what we can then do is work out what this angle here is going to be. Now, if this side here is 90 degrees, again, if you're not sure what I'm talking about, so I'll highlight it here. So if this angle here is 90, then that means that this angle here is going to be 90 as well. Now, if I just highlight this angle, and to work out this red angle, well, that's going to be 90 minus y. And note that this red angle here is the same as this angle here. So therefore, we have then gone on to prove that those two opposite angles, or the angle at the tangent and the angle in the opposite angle in the triangle, are equal. So now let's move on to cyclic quadrilaterals. Now, in a cyclic quadrilateral, it states that an opposite angles in a cyclic quadrilateral are supplementary. In other words, add up to 180. So for example, this angle here, if I just call that A, and this angle B, well, A plus B equals 180. And similarly for C and D, which are also opposite, C plus D equals 180 degrees as well. So let's go on to prove that as well. So if I start by, first of all, let's label these points. So let's call this A, B, C, and D. And if I just mark where the center is going to be, and I'll just label that as O. Now, the next thing I then need to do is to draw a line from one of the points to the center, and then like so. Now, if I call this angle at A X, then this angle here is going to be 2x, because of the arrowhead theorem. And also, if I call this angle here y, then that means that this angle here is also an arrowhead, so that's going to be 2y. Now, from this, if I then take this angle here at the center, I then know that 2y plus 2x, or actually let me write that the other way around. So let's write 2x plus 2y must add up to 360, because it angles around a point. So therefore, if I divide both sides by 2, x plus y equals 180. And what sides are x plus y? Well, this is x and this is y. So therefore, as the opposite angles are x and y, then the two must add up to equal 180 degrees. And again, if I wanted to prove B and D both add up to 180, or the sum adds up to 180, then all I need to do is flip the diagram and then draw the arrowhead going in the other direction, or pointing upwards, I should say.